Hello everyone, my name is Professor Anil Fernando from Computers and Information Science Department in the University of Strathclyde in Glasgow, UK. So today I'm going to talk about an interesting topic which is based on leveraging electric vehicles and machine learning for sustainable peak energy demand management in the UK. So before we start the presentation, I would like to give you some kind of introduction to my research background. So I'm leading the multimedia research group in the Computer and Information Sciences department in University of Strathclyde. So I have 20 plus researchers working on different aspects of media. Mainly, people are working on video coding and communications, which involves video compression, semantic communication, 6G media applications, and also some other people are working on machine learning for different applications. Main applications include energy systems, digital health, and media processing applications. And some people are working on future digital advertising again based on vision processing and machine learning and AI tools. And finally, the other main domain is the quantum communications, where we look at how quantum communications can be tailored down to transmit media for different applications. And here is a snapshot of how the research has been progress in different domains. Mainly, majority of the work is based on media communications, which involves different aspects of video and image communications, and energy management applications, how AI and machine learning can use in energy management and energy aware networks, and how energy can be utilized in a more sustainable manner. And in terms of digital health, so we are looking at how AI can be used in different applications and how XAI techniques can be used to identify the reasons behind of the decisions taken by the machines. And then some people are looking at next generation networks, which involves quantum communication and neuromorphic computing and IoT for media applications. And finally, a little group is looking at how AI can be used in insurance and finance sector. So to start with the presentation, so the today's topic is how important is the peak power management in UK. The presentation that I'm talking about today is not limited to UK, but here we consider UK as a use case because our main research is developed based on UK statistics. So to start with the background, so as you may know, how important is the peak energy management management is important in the power sector. So mainly because of the every country has some kind of peak at some point of the day in the energy network. So it's important to not to have a high peak power demand or generation at a given time, mainly because of the cost savings, because time of pricing is going to have a major problem in the energy management, and also demand charges. So, for example, if the demand is high, the network has to charge a certain higher percentage for the tariff, which is going to be a difficult task for energy management. And in terms of the engineering aspects of the peak power management is needed because of the grid stability. To maintain the stability and reliability of the network is important. If we somehow can minimize the peak demand or peak generation, it will have a sustainable solution for grid stability and reliability management. And finally, also we need to look at the equipment reliability. But equipment reliability is also important in energy network. So if we can bring down the peak demand or peak generation, it will have a significant impact on the equipment reliability. And also in terms of the sustainable energy management, is having a low peak or flat, ideally flat demand and generation will be quite helpful for a sustainable energy management, which will eventually generate a lot of impacts on the greenhouse gases as a whole. So these are the advantages of having a low peak power demand over the peak generation. So having said that, I mean, our focus here is to manage the peak power demand of using some kind of machine learning optimization. And our focus here is like electric charging vehicles, which will eventually, we propose that these electric vehicles will become a source and a sink for the energy network. So we'll try to use each and every electric vehicle to contribute to the peak power management using machine learning. So why we propose electrical vehicles or EVs as a decentralized energy storage? Because this each EVs will come up with a good battery capacity for charging and discharging. So we propose like this can be used as a decentralized energy storage for energy storage and also to supply the energy as the network needs. So we'll again uh, try to use the machine learning optimization based on our mathematical modeling, which uses Bayesian probability models to enhance the energy distribution efficiency. And we try to predict what kind of vehicles will be available for energy supply and also energy demand. So this will eventually help to reduce the fossil fuel dependency, shifting towards renewable energy for peak power management. And also another goal of the technology is to enhance the grid stability, like I mentioned before, balancing supply and demand to the electric vehicle-based energy trading model. Innovative EV income model is also we try to propose in the future, so which provides some kind of incentives for electric vehicle owners with dynamic pricing and contribution bonuses and battery health subsidized. Furthermore, real-time data and predictive analytics will also be used through machine learning again with mobile computing technologies to support this technology, and scalable and sustainable framework aligning financial incentives with net zero carbon goals will also be a goal of this study. And digital technical and real world implementations will also be considered in the proposed framework, providing the insights for researchers, policymakers, and energy professionals. And finally, economic and environmental benefits will be the main target of this proposal, which will include lower energy cost, reduce CO2 emissions, and increase clean energy participation in the future. So, like I explained before, our main focus is the electric vehicles as a decentralized energy storage and machine learning and predictive analytics, which uses probabilistic models to optimize energy distribution and user participation. An innovative income model is also proposed here, which provides incentives for electric vehicle users to supply and demand based on pricing mechanism will be developed based on the supply and demand, which will help them to manage their energy supply and demand, which provides eventually some kind of incentives for their own energy pricing. And towards the end of this project, we will be looking at real-world use cases and studies and simulations based on these technologies. And also, we try to address the key challenges in the future, overcoming battery degradation, user adaptation, and grid integration barriers for sustainable energy management with the electric vehicles. So look at a typical peak demand curve, which is shown here. So as you can see that this peak demand can be varied depending on the country, and here this is present in the UK as a use case. So you can see that between 11 to like 5 p.m. The peak demand is happening in the country. So first of all, we have to understand where the peak is happening, and then propose the technology to minimize that peak using the proposed model. So in maintaining this peak demand, so we have a lot of problems. Current dependency on fossil fuels, how this peak demand is supplied at the moment using the natural gas, so which is kind of a primary source for managing the peak demand. So this will impact significantly on carbon emissions. Increased fossil fuel usage leads to higher carbon dioxide emissions, which is going to be a nonlinear, which is going to be a nonlinear behavior. So conflict with the sustainability goals. So like you know that SDG seventh goal is affordable and clean energy, which will have a significant conflict with the sustainability defined by the UN. So need for an alternative solutions. So that's why we have considered electrical vehicle-based decentralized storage for cleaner, sustainable, and energy management as a solution. So, what are the financial impacts? Current issues with the big demand in the UK has a lot of problems, a lot of impacts. So, which is the financial impact? High energy cost, expensive grid management, infrastructure investment needs. So these are the main financial impacts. And non-financial impacts includes grid stability issues, which is like high peak demand, put stress on the electricity grid, increasing the blackout risk, and energy security concerns, and heavy resilience on imported energy sources makes the system vulnerable. And environmental impact is another major problem. Increased carbon emissions, fossil fuel usage for peak power management contradicts with SDG number 7, affordable and clean energy, like I mentioned before, and slow renewable integration. So the rigidity of current peak demand solutions hinders the adaptation of cleaner green energy sources. So the economic impacts fluctuating the market price, peak demand voluntarily affect the wholesale energy cost and the consumer tariffs, strains on public funds. This is again a major problem for the governments to subsidize for peak energy management increases financial burdens, opportunity cost for cleaner alternatives. So delayed transition to sustainable EV-based energy solutions result in long-term financial and environmental losses. So, how to mitigate this problem? One way to look at the problem is BESS as a benchmark solution. What is BESS? Is like battery energy storage system, which can be used as an advanced energy storage technology that allows excess electricity to be stored and used when demand increases. So, excess energy utilization can be stored, the surplus energy generated from solar, wind, and hydropower for later use. So this can be effectively used for peak demand management. So discharges storage energy use during the high demand period to stabilize the grid. So this is one of the solutions. So it will eventually help to grid management with flexibility and stability and support for electrification, enhance the reliability of electric vehicles, charging networks, and so on. So, what are the challenges of using BESS as managing the peak demand? So, high initial investment is needed, extensive battery technology and infrastructure setup cost, and environmental impact of battery production. So, mining and disposal of battery materials contribute to pollution and ecological damage. Limited storage capacity, batteries can store only a finite amount of energy, requiring multiple units for large-scale deployment and degradation over time. So battery performance decline with repeated discharge and charge cycles, reducing the efficiency. Lithium supply and restore constraints depends on rare materials like lithium, cobalt, and nickel raises sustainability concerns. And some more challenges, disposable and recycling challenges, safe and efficient recycling of used batteries remain a significant issue. Grid integration complexity, energy losses during storage, security and safety risks, dependency on renewable energy variability. So these are the main challenges of using BESS as managing the peak power demand. So the main problem is, like I explained before, the cost factor. We have to tailor-made these best systems for peak power management, which will increase the significant investment and high risk of managing these centers in the long run against natural disasters and man-made disasters. So, what is the research gap? Research gap is fossil fuel dependency, lack of EV incentives, grid instability, machine learning underutilization, and need for a scalable model. So, these are in terms of the research of why we are doing this, and these are the possible research gap which we need to close by introducing a new technology. So let's look at the smart cities and smart transportation. So optimizing in urban energy usage, AI-driven systems can enhance energy efficiency in cities. Smart grid integration like real-time data management balances supply and demand. EVs as mobile energy units. So since the vehicles are moving, so which we can consider as mobile energy units, electric vehicles can support grid stability with energy storage. Reduce traffic congestion, AI-based transport systems can improve mobility flow, which will eventually increase the energy management. Sustainability and net zero goals, smart transportation minimizes the carbon dioxide emissions. So now our proposal is to use EV as a decentralized energy storage. So EVs as mobile batteries. So since every car will come up with a battery, so which we can use to control the energy management without any capital investment. So vehicle to grid technology is a prominent technology which enables bidirectional energy flow, stabilizing grid fluctuations, reducing grid strain. So EVs can help balancing out supply and demand. Enhancing renewable energy uses, EVs store excess renewable energy and release it when it is needed. So financial incentives for EV owners so that they will be motivated to participate in these national exercises. So what are the limitations of current incentive models? Lack of dynamic pricing. So mostly we have a static pricing mechanism, limited financial incentives, battery degradation concerns, restricted off-peak charging windows, low adaptation rate. So these are the main limitations of current incentives for EV users. So in related to that, we propose EV income model. So which will include like dynamic pricing system based on the supply and demand, contribution bonuses. So people will be given bonuses or high incentives when they sacrifice the battery for storage and supply. Battery health subsidized provides financial support to offset battery degradation concerns. Real-time data optimization uses AI-driven analytics to forecast energy demand and optimize incentives. Scalable and sustainable solutions aligning financial rewards for energy efficiency to storage, widespread EV participation. And then we are talking about predictive analysis using machine learning. So what we are trying to do is we are trying to use the machine learning and with together with the probabilistic models based on Bayesian probability decision making engine, and we develop some kind of mechanism to predict how the energy demand can be forecasted and then how the users can be informed to participate in the dynamic electric tariff structure to supply and to source and sink the energy from the network. So what we propose is a bidirectional energy flow using vehicle to grid technology. So grid stability enhancement, optimized energy distribution, renewable energy integration, economic and environmental benefits. So these are the prime concerns of the proposed system, which will eventually help to manage the energy in real time together with supply and demand from the EV. So the economic impacts of earlier simulation shows that the proposed system can reduce the operational cost by 30%. So it doesn't need any major capital investments. Revenue generation for EV user owners. collectively can earn up to 1.2 billion annually by 2050. So job creation and market growth, expanding EV infrastructure boosts employment in energy and technology sectors, which will eventually help all EV users to participate and create be part of the energy management and play their own role while they get some additional benefits from the network itself. Low energy cost for consumers, efficient energy distribution reduces electric prices, which will also help to bring down the production cost as well as maintenance cost and eventually help the environment to be more sustainable. Increased investment in sustainable energy encourages funding for smart grids, renewable energy, and AI-driven optimization. Environmental impact is the main focus here. So the proposed system will help to reduce the carbon emission by 50% in 2020 in 2050, and this is based on our simulation carried out over the last few months. So less fuel dependence, reduce reliance on the coal and gas powered energy production, increase renewable energy utilization, smart grids, optimize solar and wind energy storage in EVs will help to reduce the greenhouse impact from the fossil fuels. Lower urban air pollution, reduce emissions, improve air quality and public health, and sustainable energy transition supports the global net zero and climate action goals. So towards the policy and infrastructure development, so our proposed system will help to propose a dynamic tariff implementation, the policies to support real-time pricing of for energy demand management, electric vehicles charging infrastructure expansion, increase deployment of smart charging stations nationwide, which will eventually generate some jobs and business models for local communities, government incentives and subsidized financial support for EV owners participating in energy trading, so data privacy and security regulations, ensuring compliance with GDPR FOIA during development, renewable energy integration, the policy framework to promote EV grid synergy with solar and wind energy. So what are the challenges? So this also comes with some challenges. Challenges include user adaptation barriers, limited awareness and hesitation among EV owners to participate in energy trading, battery regulation concerns, fear of accelerated battery discourages EV owners from discharging energy, regulation and policy gaps, lack of standardized policies for EV grid integration and incentive structures, data privacy and cybersecurity, ensuring secure handling of user and energy consumption data and GDPR compliance, infrastructure and grid stability, scaling up smart charging infrastructure and ensuring grid reliance for widespread vehicle to grid adaptation. So what are the future research and recommendation? So enhancing AI and machine learning models, improving predictive analytics for real-time energy demand forecasting, developing advanced intensive structures, exploring more dynamic pricing strategies to boost EV participation, battery technology innovations, so research on existing battery lifespan and improving energy storage efficiency, scaling vehicle to grid infrastructure, expanding smart charging networks to support widespread EV grid integration, policy and regulatory frameworks, establishing standardized policies for secure, fair, and sustainable energy trading. So, what are the actions to call? Industry collaboration is needed. Engage energy providers, EV manufacturers, and policymakers to drive adaptation. Investment in smart infrastructure, expand smart grids, EV vehicle to grid technology, and AI-driven energy optimization. So, policy implementation, uh, advocate for dynamic pricing, EV incentives, and regulatory framework. Public awareness and education, promote EV energy trading benefits to increase user participation. Scaling sustainable energy solutions, commit to a long-term transition towards a greener, smarter energy system. So what are the conclusions and next steps? So here we propose electric vehicle as a as an entity for energy management, which can provide the energy to the network and also taken the energy from the network for charging and discharging of the battery. So therefore, the conclusions and next step is to consider the following. Electric vehicles as a key energy asset. Electric vehicles can revolutionize peak demand management through vehicle to grid integration, machine learning for optimization, AI-driven energy forecasting enhances grid stability and efficiency, financial and environmental benefits. Dynamic pricing models create financial incentives while reducing the carbon emissions. Policy and infrastructure development. So governments must implement supportive regulations and expand smart grid networks. And future action plan is to focus on scaling adaptation, refining incentive models, and advancing research for long-term sustainability. So thank you very much for the presentation.